At 7:41 a.m. on the 8th of May, 2026, the delicate boundary between routine geohazard monitoring and human tragedy collapsed on the remote island of Halmahera. This tragic event was not an instantaneous, unpredictable anomaly of nature. Rather, it was the climax of an escalating geophysical sequence that had been actively detected, mapped, and recorded for weeks beneath the fractured terrain of North Maluku. When the catastrophic phase of the eruption occurred, 20 individuals were situated well within 4 kilometers of the highly volatile active crater of Mount Dukono. Within minutes, 3 of those individuals would lose their lives, highlighting a critical and deeply complex failure in geohazard risk compliance, public communication, and the human perception of geological peril. In the framework of disaster risk assessment, risk is defined as the mathematical intersection of hazard exposure and vulnerability. In this instance, the hazard was highly monitored and well-defined, yet the artificial inflation of the exposure variable through active entry into the exclusion zone turned a manageable threat into a localized catastrophe. Standing at an elevation of 1,185 meters above sea level, Dukono represents a classic open conduit volcanic system. Unlike dormant stratovolcanoes that remain quiet for centuries before undergoing sudden, highly explosive reactivation, Dukono has existed in a state of near-continuous eruptive activity since 1933. This 93-year period of persistent activity defines the volcano's unique operational baseline, characterized by a steady-state magmatic plumbing system. At the center of this dynamic engine lies the Malupang Wariang crater, a massive steep-wall depression measuring approximately 360 meters in width and 230 meters in depth. Under baseline conditions, the crater functions as a highly efficient pressure release valve for the underlying magmatic column. The system continuously degasses, emitting steam and moderate ash plumes that typically rise between several hundred to 2,000 meters into the troposphere. This steady, low-level release of kinetic energy, thermal radiation, and volatile gases, primarily water vapor, carbon dioxide, and sulfur dioxide, has historically prevented the catastrophic accumulation of internal magmatic overpressure. However, in late March 2026, the established equilibrium of this open conduit system underwent a profound and ominous geomechanical shift. Monitoring instruments managed by Indonesia's Center for Volcanology and Geological Hazard Mitigation began registering highly anomalous seismic datasets that pointed to deep-seated structural changes. In a single 24-hour window, the local seismic network recorded 199 high-frequency volcanic tectonic earthquakes, a massive spike that shattered the volcano's historical baseline. Unlike low-frequency harmonic tremors, volcanic tectonic earthquakes are characterized by sharp, impulsive arrivals that indicate the physical fracturing of brittle rock. This sudden seismic acceleration signaled a rapid migration of fresh, volatile-rich magma from a deeper reservoir into the shallow conduit, accompanied by severe mechanical blockages. As the fresh magma ascended, it encountered older, highly viscous crystal mush, causing structural blockages within the primary conduit. By April, the internal dynamics of the system grew increasingly volatile. The volcano's heartbeat became rapid and chaotic, culminating in 7 major explosive pulses in the final week of the month. The seismic data was no longer indicative of a stable open conduit system. Instead, it was signaling a rapid transition toward closed system dynamics and a massive buildup of shallow lithostatic overpressure. Recognizing the extreme hazards associated with ballistic projection, toxic gas accumulation, and pyroclastic density currents, volcanologists and local authorities strictly enforced a 4-kilometer exclusion zone around the active Donvent. This buffer zone, derived from historical eruption maps and advanced numerical models of ballistic trajectories, was designed to keep the public at a safe distance from the volcano's unstable summit. The critical tension between natural geodynamics and human risk perception reached its absolute breaking point on the morning of May 8th. Prior to the explosive event, the immediate microenvironment around the slopes of Dukono experienced a sudden, profound, and highly unnatural quiet. Local guide Alex Jangu, who had spent decades navigating Halmahera's volcanic terrains, recognized the immediate danger of this sudden silence. To an experienced volcanologist or field guide, the cessation of visible degassing is not a sign of safety or dormancy. Rather, it is a classic, terrifying precursor of conduit sealing. This phenomenon occurs when the volcanic vent becomes temporarily obstructed by cooling magma, collapsed crater walls, or mineral crystallization. When the gas flux drops toward zero, the gas cannot escape, and the internal pressure beneath the lithostatic plug begins to rise exponentially, because the rate of pressure increase is directly proportional to the difference between the incoming magmatic gas and the gas escaping the system. Because the escape route was blocked, the pressure inside the volcano was rapidly building toward a critical threshold. Recognizing that the volcano was holding its breath, Jong-gu issued an urgent warning to his group, explaining that the absence of surface emissions indicated that the internal pressure of the shallow magma chamber was reaching a critical explosive limit. Despite these clear warnings, the local guide's intuition, and the established scientific hazard boundaries, the group of 20 individuals comprising 9 international tourists and 11 local guides decided to proceed past the marked safety perimeter. This fateful decision highlights a well-documented phenomenon in disaster psychology: risk normalization. In highly active volcanic zones, the constant low-level activity can lull visitors and untrained guides into a false sense of security. Because the volcano has erupted safely for decades, visitors assume that the hazard is predictable and manageable, failing to recognize that volcanic systems are highly nonlinear and prone to sudden catastrophic state shifts. The desire for unique close-up media capture and the thrill of conquering an active crater ultimately overrode established scientific warnings. At precisely 7:41 a.m., the trapped energy within the conduit violently breached its structural constraints. A rapid swarm of 42 explosive earthquakes shook the volcanic edifice in a span of seconds, culminating in a powerful phreatomagmatic eruption. This violent mechanism occurs when ascending magma directly intersects a shallow groundwater table. The resulting thermal shock initiates a process known as fuel-coolant interaction. When the boiling magma contacts the cold groundwater, a thin vapor film initially forms between them. As this film collapses, it triggers rapid heat transfer rates, causing the water to flash into superheated steam. The volume of the water expands almost instantaneously by a factor of nearly 1700, generating an intense thermodynamic shockwave. This explosive expansion shattered the overlying conduit rock and the ascending magma column, pulverizing the material into ultrafine particles and propelling a dense, tephra-rich ash column 10 kilometers into the atmosphere. The eruption also launched heavy ballistic blocks, some the size of small vehicles hundreds of meters from the vent, in parabolic trajectories. The resulting column was not mere smoke. It was a high-velocity, highly abrasive mixture of superheated gases, pulverized country rock, and sharp volcanic glass. The physical consequences of entering this active hazard zone were swift and absolute. 2 Singaporean nationals and an Indonesian citizen were caught in the immediate ballistic and thermal zone near the summit and perished from a combination of severe impact trauma and thermal inhalation. 5 other members of the group sustained severe physical injuries from falling ballistics and hot ash, while the 15 remaining survivors were evacuated in a state of profound psychological shock. Rescue and recovery operations on the upper slopes remain highly restricted due to the ongoing threat of secondary phreatic explosions, slope instability, and lethal concentrations of toxic gases like sulfur dioxide and carbon monoxide, settling in low-lying depressions around the crater rim. This tragedy exposes the deep systemic risks associated with the unregulated expansion of extreme volcano tourism. Geotourism offers invaluable educational opportunities and vital economic support to remote communities. Yet without strict regulatory oversight, it can easily commodify highly volatile environments. Active volcanic systems possess highly non-linear risk profiles. Conditions can transition from baseline passive degassing to lethal explosive eruption within a matter of seconds, leaving zero margin for evacuation once an event begins. This incident underscores the urgent need for local governments to implement enforceable legal boundaries around active volcanoes, coupled with real-time electronic geofencing to alert authorities when exclusion zones are breached. The disaster at Dukono is a sobering addition to a long historical record of sudden-onset volcanic tragedies where hazard zones were breached. In July 2019, a sudden paroxysmal eruption at Italy's Mount Stromboli, another classic open conduit system, caught hikers completely unprepared, highlighting the extreme speed of open conduit explosions. Similarly, the 2014 eruption of Mount Ontake in Japan resulted in 57 fatalities when a phreatic explosion occurred without clear seismic precursors, catching hundreds of hikers on the summit during a holiday weekend. Most notably, the 2019 Wakari White Island disaster in New Zealand demonstrated the devastating kinetic and thermal power of shallow hydrothermal eruptions, where a sudden blowout of superheated acidic steam and ash killed 22 people. The common denominator across all these events is the extreme velocity of the eruptive mechanism, emphasizing that real-time monitoring systems are only effective when combined with absolute, uncompromising compliance with established exclusion zones. To fully comprehend the scale of these events, we must examine the broader geodynamic framework of the region. The Indonesian archipelago is situated at the complex convergence point of four major lithospheric plates: the Pacific, Eurasian, Indo-Australian, and Philippine sea plates. Specifically, Halmahera lies within a highly unique double subduction zone in the Molucca Sea, where the Molucca Sea Plate is subducting simultaneously to the east beneath the Halmahera Arc and to the west beneath the Sangihe Arc. This tectonic collision squeezes the subducting slab from both sides, driving intense partial melting within the mantle wedge. The resulting magma is exceptionally rich in water and other volatiles, creating a highly pressurized, explosive magmatic source. This continuous, large-scale tectonic deformation makes the region one of the most volcanically active zones on Earth, ensuring that the geodynamic systems driving volcanoes like Dukono remain constantly charged with energy. By the 9th of May 2026, Dukono's eruptive activity remained highly elevated. Continuous ash emissions drifted northward, causing significant ashfall in the city of Tobelo and disrupting local aviation corridors. Volcanic ash is composed of highly abrasive silica particles with a melting point of approximately 1200 degrees Celsius. When ingested by modern jet engines, which operate at temperatures exceeding 1400 degrees Celsius, this dust melts instantly and solidifies as a glass-like coating on the turbine blades, causing engine stall and complete power loss. This atmospheric hazard has forced aviation authorities to reroute regional flights, while the Level 2 alert status and the 4-kilometer exclusion zone remain strictly in force on the ground. The data confirms that the monitoring instrumentation operated flawlessly, providing clear, actionable indicators of heightened risk. The challenge we face is not a limitation of our scientific tools, but the critical necessity for human behavior to align with scientific warnings. Understanding these profound planetary systems requires a perspective grounded in empirical data, physical mechanics, and structural geology. For those who seek a rigorous analytical approach to the deep geodynamic forces shaping our world, American Sky Brief offers an uncompromising science-first perspective. From analyzing regional tectonic stress to tracking complex atmospheric lithospheric interactions, we decode the underlying physics of our changing planet. Subscribe to the American Sky Brief platform today to access detailed, continuous analyses of the geological and meteorological events defining our global landscape. The Earth is constantly shifting. Staying informed through verified empirical data is our most reliable guide to navigating these natural dynamics safely.